Hello everyone, my name is Chakapan Chanpilom. Today I am pleased to present our research titled Optimizing the One-Dimensional Cutting Stock Problem with Slow-Moving Inventory and Product Substitution Consideration in the Steel Industry. The agenda for today's presentation consists of five key parts. It is a problem description, research gap, problem formulation, pseudocode for cutting stock optimization, result, and finally the conclusion. For our case study, we utilize real-world data obtained from a steel manufacturing company in Thailand. The production process begins with the transformation of steel booms. These booms are heated and rolled into an S-roll length, or we call ARL. Subsequently, they are fed into a cutting machine to be processed into specific product lengths based on customer demand. Regarding the company's current situation, inventory is categorized into four quadrants based on the order frequency and volume. Quadrant 4 represents slow-moving stock categorized by low demand frequency and low order quantities, which significantly drive up holding costs. To address this, the company aimed to utilize this slow-moving stock as an overgrade substitution to minimize total holding cost. Additionally, they are looking to explore customized S-roll length ARL to mitigate trim loss. Currently, planners spend 4 hours or more manually generating a single cutting pattern, which represents a substantial waste of time and operational inefficiency. The physical configuration of the cutting machine is shown on the slide, where the raw material is fed from the right-hand side until it hits the saw gate stopper. As illustrated in the figure, the cutting system consists of three saws: one fixed hot saw, we call FHS, and two movable saw, we call MH1 and MH2, positioned to the right of the fixed saw. Additionally, the machine features three adjustable stoppers located to the left of the fixed saw. The operational constraints for these stoppers are as following this. Stopper 1 must be positioned at a minimum distance of 6 meters from the fixed saw. Stopper 2 requires a minimum clearance of 1 meter from stopper 1. Place it at least 7 meters from the fixed saw. Similarly, stopper 3 requires 1 meter clearance from stopper 2, positioning it at least 8 meters from the fixed saw. Regardless of the selected stopper, the maximum product length is restricted to 18 meters. For the movable saw, movable 1 must maintain a minimum distance of 6 meters from the fixed saw, while movable 2 can be adjusted with a range of 6 to 18 meters relative to movable 1. However, the combined product length processes by both movable 1 and movable 2 cannot exceed 24 meters. Furthermore, the initial and final sections of each feed, the head and tail cuts, are treated as scrap and must be processed using the stopper and the fixed saw. Crucially, because the system utilizes two cooling beds to lower product temperature post-cutting, Each feed can accommodate a maximum of only two distinct product sizes. These strict mechanical specifications significantly elevate the complexity of the cutting pattern generation, making the identification of on the optimal pattern to minimize total waste and critical production challenge. The problem description and machinery condition, we identify several key research gaps. First, this study addressed a specialized problem in the steel industry by, by explicitly mathematical modeling based on real machine constraints. By introducing adjustable as row linked AIL, we propose a novel mathematical formulation that incorporate these soft constraints. Furthermore, we applied both product substitution and the customized AIL concept to simultaneously minimize trim loss, overproduction, machine setup times, and total operation costs. Finally, considering the NP-complete nature of this problem, a traditional brute force approach failed to find optimal solution with the required 4-hour operations windows. Therefore, our research focused on developing an efficient optimization method capable of delivering high quality solution within this strict time limit. Whereas the problem mentioned previously, we formulate our mathematical model by defining an objective function aimed at minimize the total operational cost using a weighted sum approach. As shown on the slide, the objective function consists of 6 key components. The first one is a trim loss. This is calculated by subtracting the total waste of the finished products across all feeds within a pattern from the initial bloom weight, and then multiplying the result by the usage frequency of the specific pattern. The second term is a overall material. This represents the excess volume produced beyond the customer acceptable limit. Based on company policy, a maximum overproduction tolerance of 5% above original demand is permitted. Next term, it is cutting time. This is determined by the total number of cuts executed across all feeds within a pattern, multiplied by its usage frequently. Next, it is the product substitution term. This tracks the total number of slow-moving stock AL bar of a specific length and grade that are utilized in the production run. Next term, it is the standard AL usage. This counts to total number of standard stock AL bar of a specific length and grade used. And the last term is the customized ARL. This refers to the total length of newly adjusted as row length, which can deviate either longer or shorter than the standard baseline, providing they remain with acceptable operational tolerance. Crucially, product substitution and standard ARL usage are assigned a minimized sign in the objective function. Since our primary goal is a minimization, these negative coefficients act as incentive, encouraging the mathematical model to maximize the utilization of slow-moving stock and standard inventory. This slide outlines the order fulfillment and piece counting constraint. Equation 1, the order fulfillment constraint ensures that the total volume of finished products meets or exceeds the customer demand. The equation number 2 is a binary indicator variable. It's equal 1 if the cut piece length match the specific order product length and 0 on otherwise. Equation 3, total quantity. This quantify the total number of finished steel products of a specific length obtained from the cutting process. And equation number 4, the form length variable. This defines the exact length of the cut piece at a specific sequence within a given feeding cycle using a particular cutting pattern from an ARL bar of a designed length and type. On this slide, it is inventory control and solve custom ARL constraint. Equation number 5, slow-moving stock availability constraint. It shows the total number of slow-moving ARL bar of length A and grade G utilized must not exceed the existing inventory quantity available in the warehouse. Equation number 6 and 7, non-negative constraint. The number of standard stock ARL bar of length A and grade G utilized, as well as the number of newly rolled custom length ARL bar utilized for grade G must be greater than or equal to 0. And equation 8, customized ARL generation equation. This equation governs the generation of new cutting ARLs, allow them to deviate either shorter or longer from the baseline standard length within the permissible limit. Equation number 9, pattern length capability constraint. The total length of all products allocated within each cutting pattern must be less than or equal to total available length of the corresponding ARL bar. On this slide is show technical machine boundary and setup constraint. Equation number 10, the first cut piece of the initial feed is structural waste and cannot be used. Equation number 11 is mean the final feed cycle yield no usable product for sequence cut 2 and cut 3. Equation 12, it is the range of cut 1 when stopper engage or disengage. Equation 13 is mean the range of length of cut 2, and 14 equation, it is the range of length of cut 3, and 15 it is the total length of cut 2 and cut 3 no greater than 24, and 16 equation 16, it is a reflex penalty time for changing blade setup. On this slide, it is the objective weight distribution constraint. Equation number 17 and 18 is the total weight must be equal 1 and the range of weight is between 0 and 1. On this slide, it shows pseudocode for cutting stock optimization. Step 0, data preparation. You should to import customer order current steel stock, and machine constraint. After that, generate all possible blade position, then plunge in visible blade position, and after that, generate all pattern based on plunge blade position. And then start with step 1, decision optimization mode. If the number of patterns before this step is low, use brute force mode. The brute force mode will start from the generate or possible combination of cutting sequence based on the above pattern. Then calculate the total cost for each combination, and then save the combination with the lowest total cost. If the number of the pattern is high, you will use the ACO and or AND colony optimization mode. It starts from a multiple AND explore path combination to build solutions, calculate total cost and evaluate performance, and then deposit pheromone on path that result in a lower cost and evaporate pheromone. And then following and generate paths based on pheromone level, focus on cost-effective path, and then select the best solution found by the colony. Next is step 2, it is evaluation. Evaluation calculation, the total objective value will be calculated following the objective function as we mentioned before. And the step 3, it is reporting. Output the optimal cutting pattern will be generated, and specify the number of iteration or repetition required, and detail the necessary steel stock, AIL, or substitution to be consumed. That's it. That is the pseudocode for cutting stock optimization. After implement the real-world data from the case study, we evaluated the performance of both brute force approach and ant colony optimization algorithm. The computational experiments were conducted by varying the number of product size from 2 to 6 to benchmark the model. We monitor several key performance indicators, including the number of available substitution, quadrant for substitution usage, the number of customized ARLs, trim loss, the total number of patterns generated, the final total weighted objective value, and the overall computational time. Our findings indicate that for the small problem instance, specifically with 2 or 3 product size, the brute force method demonstrates high efficiency, requiring only 0.01 minutes and 4 minutes to compute respectively. However, as the problem scale expands to 4 product size, the computational time for brute force escalates dramatically to 199 minutes. In contrast, ACO exhibits superior scalability and efficiency in larger problem size, required only 9 minutes for 4 minute size, 23 minutes for 5 product size, and 28 minutes for 6 product size. Crucially, the brute force approach fails to converge or complete the calculation within the company's strict 4 hours or 24 or 240 minutes time limit for a larger problem instance. In terms of solution quality, both methods yield identical total weighted objective value in small problems. However, for large-scale problems, ACO significantly out, outperform brute force by substantially reduce the total weighted objective value. Furthermore, a major highlight of our optimization model is that every experiment successful utilize quadrant 4 uh, substitution and several scenario effective integrate customized AIL, both of which were strategy completely omitted in the company legacy traditional planning process. While the ant colony optimization algorithm demonstrate high efficiency in solving large-scale problems, and analysis of the convergent curve, specifically looking at the objective value versus the number of function evaluation, reveals that the algorithm converts quite rapidly. However, it also shows a strong tendency to get trapped in the local optima. Consequently, this highlights a clear opportunity for future research, specifically in the further developing the algorithm or hybridizing it with another meta-heuristic to enhance its global exploration capability. Finally, conclusion. Applying soft constraint, product substitution, and customized AIL can reduce the total operational cost and other costs. Brute force is suitable for small-scale problems, whereas large-scale problems consume excessive time and fail to complete within 4 hours. ACO is suitable for large-scale problems as it provides acceptable solutions within the 4-hour limit. However, ACO still requires significant computation time for large product varieties, and is occasionally suffer from premature conversion and getting stuck in the local optima. Uh, the, our proposed method significantly reduces the time required to generate cutting pattern to less than an hour, whereas the manual process can take up to an entire day. The last thing it is the substitution method and customized AIL is utilized more frequently compared to before, which did not employ it. Thank you very much for your attention.